Hi, everybody. Welcome back. So far in this module, we've introduced the necessity of treating chemical reactions at a stochastic level, or at a level where we can account for some of the randomness in individual reactions, at least for some biomolecular systems where the number of molecules may be very small. This is particularly the case for RNA molecules, but also for many proteins, where the total numbers inside a cell might only be numbered in the hundreds or something like that. And for RNAs, even smaller. We've also introduced some of the basic language of probability theory and shown how a Poisson process can be a good model for a individual chemical reaction happening at a constant rate. For example, the contrived situation of synthesis of protein from a constant quantity of RNA. In the next two video lectures, we're going to expand these ideas into systems of biochemical reactions. A framework will allow us to do stochastic simulations on biochemical systems, really of any size and complexity. This first piece will be focused more on the theory in the background, and then the accompanying subsequent video will dig more into the actual implementation of an algorithm that lets us simulate these systems. So let's begin by switching over to the slides. Let's begin with a little bit of a review of what we've seen from a Poisson process, a simple model for a protein synthesis from a fixed RNA concentration, or really for any chemical reaction occurring at a constant rate. And what we can learn about that system and its relationship to mass action kinetics, which we've also discussed fairly extensively. First of all, the Poisson process, the results from the last lecture, let us describe how many molecules we expect to have as a function of time, both on average and in sort of the details of the distribution of states. And in particular, the total number of events occurring within a certain time for a Poisson process follows what we call a Poisson distribution, where the parameter is lambda equals alpha t. So a time-dependent parameter, a time-dependent Poisson distribution, or a time-evolving Poisson distribution. And one of the nice things about getting a distribution that's been well studied, that we understand, is that things like the expectation value, the variance, have known forms. In particular, for a Poisson process, both the expectation value or a Poisson distribution, sorry, both the expectation value and the variance are equal to the parameter, the single parameter of the distribution, which in this case is alpha t. Focusing on the expectation value or the average of the Poisson distribution should be alpha t. In other words, the average number of molecules we expect is alpha times time, where alpha is the probability of an individual reaction happening within some unit of time. The ODE, mass action kinetic model, can be written in a very simple form. Derivative of protein concentration with respect to time is equal to a constant multiplied by the RNA concentration, but the RNA concentration in this contrived example is fixed, constant, which means this whole term is constant. This is basically a differential equation of the form dx dt equals a constant. We integrate that and we get a linear expression. The protein concentration is a constant times time, where in both of these, there's an assumption that we're going to start at a zero concentration, start at a zero count, to simplify the result. When we do this, we notice something really important. The average number of molecules is, of course, exactly what the the mass action kinetic model gives us. Right? It gives us the average behavior without giving us the details of the distribution. It's not surprising then that they both have a linear dependence on time. It also makes this linear dependence on time make sense given the model. If we're producing a compound at a constant rate, you would expect the quantity of it to simply grow linearly with respect to time. But importantly, this allows us to directly relate the alpha, the probability of a reaction happening in a certain amount of time, to the reaction rate given in the mass action kinetic model. In fact, these two things are the same. The probability of a reaction occurring in a given time is exactly the same thing as the reaction rate, with the caveat that we often use different units to describe these. Typically, the probability of a reaction is given in terms of units of molecules per unit time, whereas the mass action kinetic rates are typically given in terms of concentrations, very often expressed in moles per liter of a per unit time. And so we have to be careful about making sure that we convert properly between units to work with in numbers of molecules compared to moles worth of molecules. And that's a significant translation factor, but easily manageable. We also learned that the Poisson process can be understood in terms of a waiting time between reactions. How long do we expect to wait for a reaction to occur? Well, the distribution of waiting times is given by an exponential distribution. And once again, the exponential distribution is well characterized with a known variance and a known expectation value. The expectation value of the exponential distribution, sorry, there's an extra t here, that I'll cross out. The parameter of the Poisson process, the distribution of times, is simply alpha, not alpha t, as it was for the number of states. The distribution, the expectation value of a exponential distribution with parameter alpha is 1 over alpha. That is, the average time between reactions is 1 over alpha. Remember, alpha is the probability of a reaction happening in a certain time, but it is also the reaction rate in the mass action kinetic model with appropriate units. This tells us another interesting thing. The average time between reactions is simply the reciprocal of the reaction rate. Once again, in order for this to be an actual average time between individual reactions, the rate must be expressed in units of molecules per second or per unit time. Whereas if we're given a rate in molar per second, then the reciprocal of that rate will be giving us the average time required for a molar worth of reactions to happen. Right? But this is really just a units conversion, and as long as we're careful about the units, we can make this equivalence. Now that was for a very particular case, a single reaction where the rate doesn't change over time. In order to make connections to more complicated systems where we have multiple reactions and where the rates and therefore the probabilities of the reactions are changing with respect to time, we need to introduce the idea of a Markov process. A Markov process is any stochastic process for which we can figure out or predict the distribution of future states, the probability of all future states, knowing only the probability distribution for the current state, what the state the system is in right now, along with a set of evolution rules. Most importantly, we do not need to know anything about the path that was taken to get to the current state. The history of the system does not impact the future evolution. Every stationary process is, of course, Markovian because the probability distributions don't change. The Poisson process is Markovian because the individual transition probabilities don't change. So they obviously can't depend on the past. But more importantly, any system of chemical reactions and biochemical reactions is also Markovian. Why is this the case? It's because reaction rates are determined by the current state of the system. It's the number of molecules present right now that dictates the overall reaction rates, which dictates the probability of a reaction happening. If the probabilities of reactions happening are entirely defined based on the numbers of molecules at that particular point in time, then the history of the state, how we got to that state, does not matter. It's a Markovian process. This Markov condition is a central link between the Poisson process and more complicated systems of reactions, as we will discuss in the next few slides. So now I'm going to introduce the idea of the chemical master equation. It's a little bit of a scary sounding name that captures a fairly simple idea when you get right down to it. Any Markov process can be described by something called a master equation. This language tends to be used primarily in the fields of physics and physical chemistry. And really simply is a fancy way of saying the rules that describe how the probabilities of the system evolve over time. How do we derive a general master equation for biochemical systems and more generally for any system of chemical reactions? Well, we're going to start off with making one common assumption with mass action kinetics. We're going to assume a fixed volume, well-mixed environment. This is not necessarily a reasonable or a good approximation for biological systems. Inside of cells are very heterogeneous environments. They are not particularly well mixed. But simplifying approximations are often necessary in developing models and can help us build connections between different levels of complexity of models. In particular, by making this assumption, this lets us have a direct link between the values that we get out of mass action kinetics and the expectation values of the probability distributions that we get in our stochastic model. And it gives us this link for the probability, right, of each reaction. The probability of each reaction is given by the instantaneous reaction rate in appropriate units, of course, and the instantaneous reaction rate is simply defined by the same rules of mass action kinetics or in mass action inspired kinetics as we saw in biochemical systems. The Michaelis-Menten equation, the Hill equation, we will use exactly those same forms to calculate these instantaneous reaction rates, and given appropriate units, those are the probabilities of each reaction, as we've seen before. The chemical master equation will then describe how the probability distributions of having various numbers of each kind of molecule vary over time. Again, making the connection back to mass action kinetics. Mass action kinetics describes how the average of these probability distributions change over time, and this is going to give us this link. This well-mixed environment, as I mentioned, is a perhaps a potential problem point in this type of model. And actually in module 3, we are going to be discussing how we can relax that well-mixed assumption for these sorts of simulations. Okay. So now let's get into how we actually can come up with this chemical or biochemical master equation. First of all, we need a way to describe the system, right? To keep track of the state of the system. And what we are going to be doing in this case is keeping track of the number of molecules of each type. I'm going to use the notation of vector x to represent this, just to simplify the notation. And if you're familiar with vector notation, great. If you're not, it doesn't really matter. The only real thing you need to remember about what this vector notation indicates in this context is that it means that we're actually keeping track of a list of numbers. The number of molecules of each type, in this case, say there are m different types of molecules, the number of the first type, the number of the second type, the number of the third, and so on. These are random variables in the sense that each representation, each experiment of the system will give different specific values for the numbers of each different kinds of molecules. And they are values that will be changing over time as the system evolves. As reactions happen, the numbers of molecules change. We are going to want to be able to keep track of those changes specifically, and we do this by describing the effect of each reaction in terms of how it changes the number of molecules. We can represent this kind of in the following way. If we start off with a system of some number of molecules described by x at some time t, if a reaction happens, then in a tiny little bit time more, we assume that reactions are essentially instantaneous, that they happen that the time it takes for the reaction to happen is much faster than the time we wait around for reactions. And so we can think of it as an infinitesimally small amount of time. We go from t to t plus dt, and this number of molecules in the system changes by adding this vector n sub j. This vector is just a description of the stoichiometry of each species in the reaction. That is, how many molecules of each type are produced as products, how many molecules of each type are used up as reactants. So we can sort of think of this vector will have the same number of elements as x, because we have to keep track of the changes to every possible molecule in the system. But many of these will be zeros, especially for a big system that has many individual molecules. If a molecule is not involved in the reaction, it has a stoichiometry of 0. It doesn't change if it doesn't change the number in the reaction, it has a value of 0. If a molecule is produced in the reaction, then there will be a positive number in the appropriate place entry in the vector n. And this will usually be 1, it will sometimes be 2, and very rarely more than that, because reactions very rarely produce more than 1 or 2 molecules of an individual type at one time. Similarly, if a molecule is a reactant, is used up in the reaction, there will be a negative entry in this change vector that again will usually be 1. will sometimes be 2, and very rarely anything larger than that. So as an example, to get a feeling for how we can represent the system, let's consider a simple enzymatic reaction. Enzyme can interact with substrate to form a complex, a binding reaction. That complex can also dissociate or unbind into the original components. The substrate can turn into the products while bound to the enzyme, and the product can dissociate or unbind from the enzyme. We have 5 molecular species to keep track of. And so our vector X would have the numbers of each of these, a 5-element vector, the number of substrate molecules, product molecules, enzyme molecules, ES, this is free enzyme, ES molecules, or ES complexes, EP complexes. Then we also have 4 reactions. The number of reactions is 4, and we have a change vector to describe each of them. The first uses up enzyme and substrate, 1 molecule of each, and produces 1 molecule of enzyme substrate complex. So we have a -1 in the substrate position, a -1 in the enzyme position, a +1 in the enzyme substrate complex position, and 0s for product and for EP. The second reaction is just the reverse of the first, and so its change vector looks exactly the same, just with all of the signs flipped. The third reaction uses up 1 molecule of ES, produces 1 of EP, and so our change vector has no effect on S, no effect on P, no effect on E, a -1 for ES, +1 for EP. And the fourth one you can work through on your own to demonstrate that this is in fact the change vector. So that was representation. How do we represent the number of molecules and the changes? Now let's think about how we discuss the probabilities. The probability of a reaction happening between some time t and delta t. We've already kind of discussed how this has to be given by the instantaneous rate of that reaction. The probability of reactions happening is kind of a function of the intrinsic rate, and so we get this general result. We can represent this in the following way. The probability that we end up in X plus Nj, that is the reaction Nj happened at time t plus dt, given that we know we started at X and T, so we were 1 reaction away from that happening at a tiny bit of time earlier, is given by alpha times dt, just as it was in the Poisson process, but with the difference that this alpha is no longer a constant. It's something that depends on the state of the system, depends on X. And we can define such a probability for every different reaction in the system. Right? So for all of the reactions in the system, we can define a probability that that reaction happens in some infinitesimal point of time. Once we have that, we can define the probability of being in a particular state at a particular time, right? By asking, what are all of the ways we can get there? And we're only going to be thinking about sort of, at this point, 1 infinitesimal time step. So we're going to assume that we know the state at a particular time, and we're just asking what's the probabilities a tiny, tiny bit later. So what we're trying to find is the probability that we're in state X at t plus dt. And there's 2 ways we can get there. One way is that we may undergo a reaction. That is, there may be some chemical reaction that happens that takes us into that new state. That's one option. That requires that we weren't in the state beforehand because a reaction was required to take us there. The other possibility is that we already were in that state a moment ago and nothing happened. No reaction occurred, so we stay there. Okay. How do we describe each of these? Well, the first, the probability that we end up in state X because a certain reaction happened, will be the probability that we were one reaction away. That's the probability that we were in the state X minus Nj at time t, multiplied by the probability that the right reaction happened. So the probability that we were one reaction away, multiplied by the probability that that reaction occurred. That product will give us the probability of getting to state X from one particular reaction. We add up that probability for the probability of getting to this state X from all of the possible reactions. So we sum up all of the reactions. Right? These are all of the ways we can move to X from a previous state. But we also have to consider the probability that we were already in state X and nothing happened. Well, again, we're going to want a product of two probabilities. The probability that we were in the right state multiplied by the probability that that the right event happened. So the probability that we were in X already, and then we need to multiply by the probability that nothing happened. What's the probability that nothing happened? Well, it's 1 minus the sum of all of the probabilities of individual reactions. So this sum of the probabilities of individual reactions gives us the total probability that something happened. 1 minus that is the total probability that nothing happened. That's what this gives. One thing that we are assuming here is that no more than one event can happen during this interval dt. Since this is being considered an infinitesimal limit, a very, very tiny length of time, this is a reasonable assumption. Okay. All right. So we have this general result, the probability that we're in state X at times t plus delta t, given by this expression here. Turns out that we can rearrange this into a very interesting form. And let's just take a look at how we might do that. Right? The first thing, oh, sorry, let me go back here. The first thing that we might do is expand this term. And so we multiply this out. What does this give us? This gives us P of xt minus P of x and t multiplied by the sum of all of these individual terms. So we expand this into a probability and a probability times a sum. We then can take this piece and move it over to this side. So we now have the probability of x and t plus delta t minus the probability of xt, and that makes this disappear, which means what we're left with is a sum of the probabilities times the reaction probabilities minus a probability times a sum of these alphas. And when we then can additionally note that both of these remaining terms have a dt in them. And so we move this over also by dividing both sides by t dt, and that makes these dt's disappear. What we're left with after that is a right-hand side, a left-hand side that has this form, p of xt minus t plus dt minus pxt over dt, and a right-hand side that has our sum of probabilities times transition probabilities minus a probability of already being in X, again, multiplied by a sum of the transition probabilities. The really interesting thing about this form is taking a look at this left-hand side. This looks just like a derivative. The value of some function at t plus dt minus the value of some function at t divided by dt, where dt is an infinitesimal limit. This is exactly what we mean by a derivative. But this isn't a derivative of just a normal function, if you will. This is a derivative of a probability distribution. It tells us how do the probability distribution, the probabilities of finding each molecule change with respect to time. Right. And this is what the chemical master equation is. It's a set of rules for how the probability distributions of finding a number of each molecular species, how this changes over time. And this evolution rule has two pieces. The first is a sum over all of the paths that lead to the state. Right? Starts off all the places where the reactions are one reaction away from getting to the state, multiplied by the transition probability. And we can think of this second sum as this should say second in the line here. Second describes all of the paths leading away from the state. We start off in state X. This sum would have all of the probabilities of moving away, and it's negative. So the overall rate of change is given by a set of essentially flows into the system minus a set of flows out of the system. And in each of these, the terms in the sum have the same general form. All right, that's the chemical master equation. In summary of what we've seen, we can take a look at a single reaction as a Poisson process, and from that find out the relationship or understand the relationship between mass action kinetics and the rates we have in mass action kinetics and the probability of a reaction happening in the microscopic view. These are just the same number, really, expressed in different units. Biochemical reactions are more complicated than this. The reaction rates change over time, and there's multiple species we need to keep track of, but they're Markov processes. The probabilities of future states are dependent only on the current state, and this allows us to compute transition probabilities, reaction probabilities, using the same mass action kinetic rules. Once we have those in place, we can derive a chemical master equation, a differential equation that describes the rate of change of the probability distribution, the numbers of all of the molecules in the system over time. What we are going to see in the next video is how we now move from this expression of the chemical master equation that's elegant and is sort of conceptually a rule, but how do we take that and actually use it in practice to be able to numerically simulate these sorts of systems. For now, and until next time, take care and be well.